Okay, good morning. Uh, so today I am going to continue my lecture on BCH code. And in the last class, we looked at double error correcting BCH code. So I will briefly summarize it so that you get some idea again. And then we'll go and talk about the general BCH code. BCH code. And so we start with the Hamming code. Okay. Hamming code HM, I can call it. Parameters. Length is 2 raised to power m minus 1. Dimension is n minus m is k, and minimum distance is 3 is t, right? We start with the Hamming code. I'm taking the binary Hamming code right now. Binary Hamming code. We know that the parity check matrix of this Hamming code can be taken as 1 alpha alpha square alpha raised to power 2 raised to power m minus 2. If you recall, this is the parity check matrix, right? So where each entry here can be written as a column vector of length n. Each alpha raised to power I is column vector of length m. Okay. So now a vector C is equal to C0, C1, Cn minus 1 belongs to Hm if and only if we know Hx transpose is Hc transpose is equal to 0. Remember a parity check matrix, right? And this gives us if and only if condition. We can take H and C transpose. So this will give us summation Ci alpha raised to power I is equal to 0 to n minus 1. This is equal to 0. And this means if and only if C alpha is equal to 0. Where Cx is the corresponding cyclic code polynomial basically. Minus 1 x raised to power n minus 1. This was the interesting observation, right? And now since alpha is a root of the minimal polynomial, but alpha is a also root of another polynomial, so minimal polynomial of alpha, so I can say that m1x will divide Cx. This implies that every element, every code word Cx is basically nothing but Cx consisting of multiples of minimal polynomial m1x. Okay. So Hamming code is a cyclic code. So our Hamming code the Hamming code HM is a cyclic code generated by generator polynomial Gx, which is actually your m1x. What is M1x? The minimal polynomial of alpha. Okay. So Hamming code is a cyclic code. Now we have taken the same approach and we added more columns into it. And double correcting Bch code, what we did, we took H to be 1 alpha alpha square dot 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 alpha raised to power 2 raised to power m minus 2, and then we took the, if you remember in the last lecture, alpha cube alpha raised to power 6 dot 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 alpha raised to power 3 times 2 raised to power m minus 2, right? So now, and suppose C is a code that we are getting from this parity check matrix. So C, a small code word, C belongs to C if and only if Hx transpose, sorry, if and only if Hc transpose is equal to 0, right? By definition of the parity check matrix. H is the parity check matrix of a code C, which is our double electroplating Bch code, right? Now, with the same analogy and the previous one, this will imply that if and only if we have summation Ci alpha I is equal to 0 and summation Ci alpha raised to power 3i is equal to 0. I is equal to 0 to n minus 1. I is equal to 0 to n minus 1. Okay, so C belongs to C. C is a code word of this double correcting Bch code if and only if these two polynomials are 0. Now that means if and only if, so we have C belongs to C if and only if C alpha is equal to 0 and C alpha cube is equal to 0, right? If and only if, now that means if and only if from the previous argument, minimal polynomial of alpha, which is m1x, divides cx, and minimal polynomial of alpha cube, which is m3x, divides cx, right? Now, this means if and only if LCM of minimal polynomial of m1x and minimal polynomial of m3x divides cx, right? Now, now both m1x and m3x are irreducible polynomials and distinct. Okay, so this implies that we have finally C belongs to C if and only if m1x into m3x divides cx, right? Thus, we arrive at the following result, which is the theorem. The double error correcting Bch code C has parameters length 2 raised to power m minus 1, which is our n minus 2m, because we have added extra rows. This is our dimension. And D at least 5 by by design, right? Here m is equal to 3. Is a cyclic code with generator polynomial gx is equal to m1x into. So this was a summary, whatever we have done in the last class. I gave you an idea why we choose alpha cube and so on. And so now we know that this is the main result. Okay. Now, so clearly we require to give you some basic uh, background on those things. Before defining the general Bch code. So go to the next. Suppose f1x and f2x are two polynomials in fqx, right? Then we can define LCM of f1 and f2 as monic. Of course, these are non-zero actually, both are non-zero. Monic polynomial of lowest degree, which is multiple of both f1 and f2. Just like integers, we have defined the LCM of two polynomials, least common multiple, right? The monic polynomial of lowest degree, which is multiple of both f1 and f2, right? So similarly, we can define LCM of several polynomials, f1, f2, ft, right? Similar definition we can give. Also note that LCM of f1, f2, f3 can also be computed like LCM of f1 and f2 with f3, right? So in general, we can write it down as LCM of f1, ft as LCM of f1 up to ft minus 1 ft. Okay, compute first pairwise. The fifth property, which is also in we have analogy with the set of integers. If f1, ft are polynomials fqx such that we can factorize them, f1 of x is equal to a1 p1 of x raised to power e11, so on, pn x e1n ft of x. Each one we can write down as a product, at p1 of x et1 en of x ETN. These are the powers, where AI is A1, AT belongs to FQ star, non-zero, elements in the finite field. EIJ, these are non-negative, and PI is monic, distinct polynomials over FQ. Okay, so then LCM can be written as of these T polynomials will be P1x raised to power maximum of P11, Pt1, and so on, Pnx of maximum of E1n, and then E. Okay, just like the number term, we have this LCM we can define. Okay. So I think now we are ready to describe general BCH code. So let me talk about it. I will give you the general parameters as well. Okay, so BCH code in general. Okay, so let alpha is a primitive elements in FQ raised to power m, primitive element. Okay, and then define mi of x as the minimal polynomial of alpha raised to power I with respect to FQ. Then we can define, just since we have the idea of double error correcting codes, right, has generated polynomial something like this, minimal polynomial of alpha times a minimal polynomial of alpha 3. In general, actually we can define it in terms of LCM of all these polynomials. So we can generalize this this result. I can write down, or I can give a definition saying that a primitive BCH code over FQ of length n is equal to q raised to power m minus 1 with design distance. This design distance delta 2 less than equal to delta less than equal to n. So delta is in our hand. That's why it is known as design distance. How many, depending on how many errors we want to correct, we can have the design distance. Query cyclic code generated by Gx is equal to LCM of MA of x, MA plus 1 of x. So MA of x is minimal polynomial of alpha raised to power a. MA plus 1 of x is equal to minimal polynomial of alpha raised to power a plus 1, and so on. M a plus delta minus 2 of x. Okay, so this is how we can define the general BCH code. We have taken this definition of the double recurring BCH code, and actually, in the same manner, we have generalized that, okay, generator polynomial will be the LCM of all these minimal polynomials. Okay, what is A? A is some number, so for some A. Okay, so this is known as narrow sense BCH code. If A is equal to 1. Okay, note that we can also write down the generator polynomial Gx, because we know the minimal polynomial definition in terms of cosets. Gx can also be written as partial product z belongs to S x minus alpha raised to power z, where S is C1 union C2 union C delta minus 1, and Cx is x q raised to power k mod n cyclotomic cosets less than 0 less than equal to k less than. So this is Curie cyclotomic coset of x mod to n. Okay, so now I am going to describe. So this is the general definition. I'm going to describe now a theorem related to the parameters of the BCH code. Especially, we can talk about dimension and the minimum distance. So one thing, we denote the general BCH code by BCH and Q delta. These are the three basic things. Length Q is the parameter, of the finite field, and delta is the design distance. So n, as you know, of course, is q raised to power m minus 1. Okay. Okay, so I'm going to write down the result. We have a theorem here. The dimension of a query BCH code of length n is equal to q raised to power m minus 1 generated by Gx is equal to LCM of max and so on, ma plus delta minus 2 of x is independent of alpha. And second thing, so there are two properties here, first and second. The dimension, which is k actually, is at least q raised to power m minus 1 minus m times delta minus 1. Okay, so basically for the general BCH code, we don't know the exact dimension. Rather, we have a lower bound. This is interesting problem, so we don't know what is the dimension in general. Okay, so let me show you how we arrive at this formula. The dimension is at least this much. So, okay, so the proof for this dimension is, so suppose Ci is the cyclotomic. Remember, so we have to work with the minimal polynomials, and the minimal polynomials can be constructed using cyclotomic coset. The cyclotomic coset of Q modulo q raised to power m minus 1 containing A. Okay, Ci is the cyclotomic coset. And if S is the set union from I is equal to A plus delta minus 2 Ci, these cyclotomic cosets, then our generator polynomial Gx can be written as LCM of partial product I belongs to Ca x minus alpha raised to power I, that is first minimum polynomial of alpha I, alpha A, then minimum polynomial, then we have the similar one for the next one. I belongs to Ca plus 1, and this is x for I, and so on. Partial product I belongs to Ca plus delta minus 2 x minus alpha raised to power I. This is how we define the general. Now this means this is nothing but partial product I belongs to S. I can take x minus alpha raised to power I, where x is defined like this, the union of all the cyclotomic cosets. Okay. Now, dimension of the code, dimension k is equal to n minus degree of the generator polynomial, the basic definition of the cyclic code, right? Which is n is q raised to power m minus 1, and minus degree of gx, we know that's the cardinality of S. Okay. So that is the basic thing. So that means dimension k is equal to q raised to power m minus 1 minus cardinality of union I is equal to A plus delta minus 2 Ci. Okay. Now note that, so note that cardinality of Ci is less than or equal to m. Okay, that's a general thing, and is equal to m. It is equal to m if GCD of I in q raised to power m minus 1 is 1. I think I just mentioned this here, and cardinality of Ci is equal to m if GCD of I and q raised to power m minus 1 is 1. Okay, so that means k is at least q raised to power m minus 1 minus summation, this will be the summation from I is equal to A plus delta minus 2 cardinality of Ci, which is at least q raised to power m minus 1 minus, because cardinality of Ci cannot exceed m, so this is m times, I can say the summation I is equal to A plus delta minus 2 m. So k is at least q raised to power m minus 1 minus m times delta minus 1. Okay, so that's how we get the dimension. Okay, this is the lower bound on the dimension of the cyclic code. Now before proceeding further, I would like to take at least one or two examples. Okay, so if we take 2 mod 15 as a, so our cyclotomic cosets will be C2, 2, 4, 8, 1, and C3 will be, cyclotomic cosets will be 3, 6, 12, 9, right? So here length n is equal to 15. Okay, delta is 3. Suppose delta is 3. So Gx will be LCM of M2 of x and M3 of x. Okay, and dimension will be, in the binary case actually we are looking at 15 minus quantity of C2 union C3 is equal to 15 minus 8 is equal to 7. The dimension turns out to be 7 actually. Okay. Similarly, we can do for other, I'll leave it as an exercise here. So if we take 3 mod 26, so we know that cyclotomic forces will be C1 is equal to C3 is equal to 139. This was the binary case actually, I should tell you. And C2 is equal to, so ternary Bch code. Code will have length is equal to 26. Design distance delta is equal to 5. I'll just write down Gx will be LCM of M1x, M2x, M3x, and M4x. So dimension will be 26 minus quantity of C1 union C2 union C3 union C4, which is 26 minus 9 is equal to 17. Here dimension is bigger than lower bound. Okay, so this is the case. Now I am going to describe one lemma which is important. First one theorem I'll just mention, and I think maybe without proof. First theorem says that in narrow sense, Curie Bch code of length n is equal to q raised for m minus 1 with design distance delta as dimension is equal to q raised for m minus 1 minus m times delta minus 1. So the bound is achieved if q is not equal to 2 and GCD of q raised for m minus 1 and e is 1 for every 1 less than equal to e less than equal to delta minus 1. Okay, so I think this is true because cardinality of Ci will be m, you remember, so we need to somehow note in this case cardinality of Ci will be exactly m, so we will be able to compute this. This is exactly equal. Now I think the second important thing about Bch code is the parameter. I'm going to talk about the distance. Okay, so now we give them one important lemma. It says that let C be a query. We are going to use this lemma in proving the minimum distance. Let C be a Curie cyclic code of length n, generator polynomial g of x. Okay, and suppose alpha 1, alpha 2, alpha r are all the roots of gx, and gx has no multiple roots, then an element cx belongs to fqx modulo x raised to the power n minus 1 is a code word of C if and only if C alpha I is equal to 0. For every 1 less than equal to I, this is the important result, Okay. Then an element Cx belongs to fqx modulo x raised to the power n minus 1, that is the Rn, is a code word of C if and only if C alpha I is equal to 0. Okay. So this is the main result that we are going to use this result. A Bch code with design distance delta has minimum distance at least delta. This is the important result. So we are saying that minimum distance of the code is at least delta. Now you see, delta is in our choice. Okay, if I want to correct 2 errors, so I know delta should be 5. So distance should be at least 5, right? So delta, that's why delta is known as design distance. So the proof is really simple. So we'll just quickly sketch the proof of this fact. Alpha is a primitive element of fq raised to power m. This is the primitive element. Okay. C is a Bch code with generator polynomial. Gx is equal to LCM of max and so on, ma plus delta minus 2 of x. So clearly, alpha raised to power a, alpha raised to power a plus 1, alpha raised to power a plus delta minus 2 are roots of gx, right? Why? Because alpha is because max is the minimum polynomial of alpha raised to power a. So alpha raised to power a is the root of max and so on. Alpha raised to power a plus delta minus 2 is the root of ma plus delta minus 2x. So these are roots of gx. Now, suppose I'm going to assume the contradiction, the contrary. Suppose minimum distance is strictly less than delta. We have to prove that the minimum distance is at least delta. We have to prove this fact that minimum distance is at least delta. But we'll assume that suppose minimum distance of this Bch code is less than delta, right? Now what happens? This implies that there exists a non-zero code word Cx is equal to C0 plus C1x plus C2x square plus dot 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 Cn minus 1 x raised to power n minus 1, such that weight of Cx is d, of course, because d is the minimum distance, right? and this is less than delta as for our assumption. Okay. Now we know that C of alpha I, so we know that C of alpha I has to 0, right? For every I is equal to A up to A plus delta minus 2. Okay. So this will give us the following matrix: 1 alpha raised power A, alpha raised power A whole square, alpha raised power A raised power n minus 1, 1 alpha raised power A plus 1, alpha raised power A plus 1 whole square, alpha raised power A plus 1 raised power n minus 1, dot 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 1 alpha raised power A plus delta minus 2, and so on. Alpha raised power A plus delta minus 2 raised power n minus 1 times C0, C1, C2, Cn minus 1 is equal to 0. So this is by definition, because C of alpha is equal to 0. So I have, I can write it down. The first one is for each I is equal to A. The first we'll get when you multiply the first row with this column, raised to power A is equal to 0. Then C of alpha raised to power, A plus 1 is equal to 0, and so on. C of alpha raised to power A plus delta minus 2 is equal to 0. Now suppose support of Cx, support means non-zero elements. Support of Cx is R, a set having I1, ID. Suppose these are the only positions I1, I2, ID, which are non-zero. So Cj is not equal to 0 if and only if J belongs to this set R. Support is this I1, I2, I3 up to ID. These are D non-zero positions, because we know that the weight of Cx is D, right? In this case, what will happen? I can write down, the only non-zero things. So we will have matrix alpha raised to power A times I1, alpha raised to power A times I2, alpha raised to power A times ID. Okay. Alpha raised to power A plus 1 times I1, alpha raised to power A plus 1 times I2, alpha raised to power A plus 1 times ID. Dot 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 alpha raised to power A plus delta minus 2 times I1, alpha raised to power A plus delta minus 2 times ID, times we have our non-zero elements Ci1, Ci2. I am only writing the non-zero things, that's all. Cit is equal to 0, right? Now since D cannot exceed delta minus 1, because D is strictly less than delta, so that means D cannot exceed delta minus 1, right? Choose first D equations of the above system. Only first D. In that case, we are left with alpha raised power A times I1, alpha raised to a times I2, alpha raised to a times ID, dot dot dot, alpha raised to a plus d minus 1 I1, alpha raised to a plus d minus 1 ID, and times ci1, ci2, all non-zero things I am writing, but only this time we are taking first d equations is equal to 0. Now this is a matrix, and I can compute the basically the determinant of this matrix. Determinant of this matrix is partial product J is equal to 1 to D. This kind of matrix is known as Van der Waals matrix, so I think I'm not going to talk about it, but it's easy to compute the determinant of this matrix. This is alpha raised to power ik minus alpha raised to power il. Since alpha raised to power ik and alpha raised to power il are distinct, so this whole thing is not equal to 0. So this is a non-singular matrix, right? So determinant is not equal to 0. Now, if determinant is not equal to 0, this will imply that the solution of this equation will be what? Ci1, Cid will be all 0, right? Which is a contradiction actually. So that means our D, should be at least D. Sorry, D should be at least delta. Okay, this is the proof that the minimum distance of the Bch code is at least delta. Now, one very special case I just want to mention here. Special case of Bch code known as Reed-Solomon code. Of course, the code was not discovered like this, but now we describe it like this. Suppose m is equal to 1. This implies that Bch code has length n is equal to q minus 1. If alpha is the primitive element of fq and mix is equal to something like x minus alpha raised to power I, therefore for delta less than equal to q minus 1, geometric polynomial we can take as LCM of x minus alpha raised to power a, x minus alpha raised to power a plus 1, x minus alpha raised to power a plus delta minus 2. Okay, or this is nothing but x minus alpha raised to power a, x for a plus 1, dot dot dot, x minus alpha raised to power a plus delta minus 2. So this is nothing but the geometric polynomial of Curie Reed-Solomon code. Okay, so length is length of this code is q minus 1. A is non-negative thing and delta lies between this and this. So I think that's all for today. Next class, we will see if we can give you the original construction of Reed-Solomon code briefly, so that you have some idea about that. Okay, and Then we'll talk about, after that, we'll talk about convolutional codes, which are very, very important. And I think if you have looked at many, the decoding of the convolutional codes, one very popular decoding is known as Witterby decoding. So we'll talk about that actually, how it is done. It was discovered by Andrew Witterby, who was a founder of the Qualcomm. And he discovered this when he was teaching coding theory course, and he was teaching convolutional codes. And so convolutional codes are basically a kind of code which involves in the construction finite automata. So, from computer science, so it's really nice, interesting way of constructing the codes. So we'll talk about these codes in the next class. So after convolutional codes, we'll look at the applications. So I think we'll be able to cover 5-6 applications, and that will end the course.